Hello viewers, we have seen in the last lecture what is three-phase star connected circuit. Let us continue with three-phase circuits today again, but let me talk about delta connected circuits today. Okay, we have seen how delta connected circuits are connected. We have seen that three coils when connected, starting point of one to ending point of other, there is a mesh connection. That is what is called as delta connection. Okay, you can see over here in this diagram also. So delta or mesh connection is normally not used in case of the distribution systems. There are reasons. I'll come back to it when we will be summing up the points regarding delta connection. Okay, so this is again the connection we'll be needing in case of three phase, that is delta. Now what is the speciality of delta we are going to see now. So this is three-phase, three-wire system because there are three vertices of that triangle, so only three wires can come out. Okay, so it is called as three-phase, three-wire system. Yes, you can see over here. This is one phase, this is another phase, and this is another phase, and this is the line terminals. So these three are line terminals. Okay, if you tap the voltage across these two line terminals, that is going to give you the same value if you tap across this phase. Okay, if you tap across these two line terminals, that is going to give you the same value as you will be tapping across this phase. Okay, if you tap between B and Y, that is going to give you the same voltage as will be across this phase. Now what do you mean by this is line voltage is equal to the phase voltage. Okay, so in case of delta, we have line voltage is equal to phase voltage. Okay, but you can see over here, whatever is the current entering over here will be divided into two. Whatever will be current entering from the line terminal will be divided into two. Whatever current will be entering from the line terminal will be divided by 2. Okay, will be divided into 2, not by 2. Okay, so what will happen over here is we consider over here a circulating current. Okay, so the current which is flowing from, let us say, R to Y is written as RY, the one from Y to B is written as YB, and the one to be flowing from B to R is named as BR. Okay, so IRY, IYB and IBR. Yes, let us proceed further. Now if you see in this diagram, IR is shown as line current, IY is shown as line current, and IB is shown as line current. Okay, you can see over here is the current flowing from R to Y in the phase is called as IRY. Okay, the another phase current which is flowing from Y to B is named as YB, and the one which is flowing from B to R is named as BR. Okay, so this is a circulating current. You should maintain the direction. So IRY like this, IYB like this, and IBR like this. Okay, so if you apply KCL at this node, it will be sum of incoming currents is equal to sum of outgoing currents. What do we get is whatever is IR is equal to IRY minus IBR. Okay, if you apply KCL at this point, it will be IY that is equal to IYB minus IRY. Okay, and if you apply KCL at this point, is at this node, it will be IB is equal to IBR minus IYB. Okay, so if you remember in the phasor diagram of star connected systems, we had taken KVL as the basic, and we started with VRY is equal to VR minus VY, and then we had drawn that 120 degrees apart phase voltages, and then phase voltages we had found out that line voltage is equal to VRY is equal to VR minus VY. So that is how we did it in case of star connected circuit systems. Over here the basis is KCL, so Kirchhoff's current law, and you will be having the KCL applied at these 3 points. You will be getting these 3 equations, and let us apply these 3 equations now. Over here we will be having these phase currents 120 degrees apart. So IRY is a phase current, 120 degrees behind it will be IYB, and still 120 degrees behind it will be IBR. Okay, so IRY 120 degrees apart, IYB 120 degrees apart, IBR. Okay, so if I write IRY as Im sin omega t, IYB will be Im sin omega t minus 120, and IBR will be equal to Im sin omega t minus 240. Okay, so what we'll be doing now over here is what I want is line current is equal to IRY minus IBR. Okay, so IRY I have with me. For minus IBR, similar treatment is opposite direction of the same magnitude, I'll be having minus IBR. Okay, and the summation of IRY and minus IBR is going to give me IR, that is line current. Okay, similarly IY is my IYB minus IRY. So IYB I already had. For I minus RY, I'll be extending this in the negative direction of the same magnitude, and the phasor sum of minus IRY and IYB is going to give me IY. Okay, similarly IB is equal to IBR minus IYB. So IBR I already had having the phase currents 120 degrees apart, and now I minus IYB I'll be drawing in the negative direction of the same magnitude as IYB, so I get minus IYB. Okay, the phasor sum of IBR and minus IYB is going to give me the line current IB. Okay, so remember it this way, that when we talk about star connected systems, it is current which is same and the phase voltages are drawn 120 degrees apart. Over here the voltages are same. You can see whatever is the tapped across line terminals is same as the phase value. So phase voltages are equal to line voltages, but there is a difference in the phase current and line current. Okay, so what we do is phase currents are 120 degrees apart, and then we satisfy the 3 KCLs applied at these 3 nodes. Okay, don't mug up the things, you just understand it better and you will be able to reproduce it as it is. Okay, again if I consider only one parallelogram over here, if I drop a perpendicular, the same treatment absolutely what we applied in case of star connected systems. So if we drop a perpendicular over here, it bisects the diagonal exactly, so this much part will be equal to IPH cos 30. So the whole line current will be equal to twice of IPH cos 30, and if I substitute cos 30 as root 3 by 2, what do I get it as? I'll be getting it as IL is equal to root 3 IPH. Okay, again 3 phase power is equal to 3 into per phase power, so that is equal to 3 VPH IPH cos phi, and if I substitute VPH is equal to VL, IPH is equal to IL by root 3 cos phi as it is, I get the same expression as root 3 VLIL cos phi. Okay, but mind well to see the expressions, both the expressions for power in case of star connected systems and in case of delta connected systems are same, but it is seen that the power consumed in delta is thrice star. Okay, so that is the reason why normally in the distribution sector star connected systems are used. Okay, so that is one of the reasons why we prefer star connected system in case of distribution networks, apart from availability of neutral. Okay, so that is about delta. Let us have a few problems solved so that the ideas will be a bit clear in your mind. A balanced delta connected load consists of 3 resistances each of 4 ohms connected to a 400 volts 3-phase 50 Hz supply. Okay, calculate phase current, line current and power consumed. Now over here you have to understand that whatever value will be given to you is always a line value, but in case of delta, line voltage is equal to phase voltage, so it doesn't matter, right? So VPH is equal to VL is equal to 400. Okay, now the per phase load is given to you as 4 ohm, that means resistive load is given to you, so ZPH is equal to 4 ohm, right? So IPH can be found out as VPH upon ZPH as 400 upon 4, that is 100 amperes. Okay, now IL is equal to it will be root 3 IPH. Okay, so line current can be found out as whatever is phase current we have found out multiplied by root 3, so that gives me 173.2 amperes. Okay, and the last thing is 3 phase power. Again I had asked you in the last lecture that always stick to either phase values or line values, don't mix it up. If I put it in terms of phase, it will be thrice of VPH IPH cos phi. If I want to put it in line terminals, it will be line terms, it will be root 3 VLIL cos phi. Okay, but always better and less erroneous method will be to put it up in case of in the phase terminals, in the phase terms. Okay, so it will be thrice of VPH IPH cos phi, it will be thrice multiplied by 400 because VPH is equal to VL in case of delta connected system, multiplied by IPH value is 100, that is what you got in the first step, multiplied by 1 by 1 because it's a resistive load given to you, so it will be the phase difference between voltage and current will be 0, so cos of phi will be equal to 1. Okay, so that gives you 120 kilowatts, right? Now the second one, 3 similar coils each having resistance of 20 ohm and inductance of 0.05 Henry are connected in a mesh to 3-phase 400 volt 50 Hz supply. Calculate the total current and power consumed. Here only the clues are given to you that what should be the first step, what should be the second step, what should be the third and what should be the fourth. Okay, so the first step is knowing the value of L as 0.05 Henry, you have to find out inductive reactance as 2 pi FL. Okay, can you do it? Yes. Okay, again point to be remembered over here is pi to be taken directly from calculator and not as 22 by 7 or 3.14. Okay, so that way you can find out inductive reactance. Then you have to find out ZPH as 20 plus JXL. Okay, why plus? Because it is inductive reactance. Okay, and XL value you have already found out in the first step. Okay, third step is IPH is equal to VPH upon ZPH. Okay, now VPH is already given to you because it is delta connected system, so line voltage is equal to phase voltage, right? So it will be 400 at an angle 0 divided by whatever value you have got ZPH as. You have to convert it into polar because in the third step you have to do the division. Okay, so that is how you can find out the value of current. Now mind well, since the voltage is taken as reference, whether it is at an angle 0 divided by the current divided by the Z, that means impedance, so you'll be getting current's angle as negative as expected, because in case of inductive circuits current has to lag. Okay, so the current's angle negative signifies that this current is a lagging one. Okay, and the last thing is three-phase power. So three-phase power is equal to thrice of per phase power. So you can put it up as thrice of VPH IPH cos phi, or you can put it up as √3 VLL cos phi. Okay, so always better if you put it as thrice of VPH IPH cos phi. Okay, find out the value, and do not forget to write the unit as watts. Okay, if the value is very large, you can put it up in terms of kilowatts, not a problem, but you have to remember that you have to write the units carefully. Okay, now let us stop here for the time being. This is about the delta connected systems. Okay, if at all you have any kind of queries, do not forget to write it in comments. Okay, thank you.